And now let's move to the next talk that will be presented by Piotr Ciochoń from SOLARIS synchrotron in Kraków, and he will tell us about new graphene method. Piotr, please share your screen. The floor is yours.
Hi, everyone. Could you please confirm that it's sharing correctly this time?
Yes, all good.
Okay, perfect. Hi, everyone. My name is Piotr Ciochoń. I'm from Jagiellonian University in Krakow, from SOLARIS synchrotron in Krakow, and from a recently formed spin-off company, BeeGraphene. Today, I want to talk to you about the future of microelectronics, the future of graphene, and specifically the future of Polish graphene. Moore's law has been defining the growth of microelectronic industry for the past decades. Originally formulated in the 60s, it predicted that the number of transistors per unit area of an integrated circuit would double every year. Although it's needed quite a few tweaks and adjustments, the law has generally held true for the past 5 or 6 decades. However, in the recent years, experts have started noticing that actually the pace of development of the industry is lagging behind Moore's predictions. While the number of transistors per unit area keeps on rising, although ever slower and at much higher cost, the other key characteristics such as single thread performance or frequency of the transistors have essentially plateaued around 2010. Even though IBM has very recently announced the successful production of the first chip in a 2 nanometer process, experts are pretty much clear that this time we're really nearing the end of Moore's law. 2 nanometers is around 10 atoms, is the thickness of around 10 atoms, and you can't really go much lower than that. This has led many to declare the end of Moore's law last year. Both professional and non-professional outlets have been writing about this. And actually, experts argued that we are not prepared for the end of Moore's law, as it was the main driving force behind the growth of the economic boom of the past decades, basically. So the obvious question is what comes next? So what can we do to keep growing the microelectronic industry, to keep having more computational power that is needed for all the brilliant AI tools that we've heard about in the last talks? Well, more and more experts, there are a few routes we can take here, but more and more experts believe that the key to unraveling the long-term growth of microelectronic industry will be the development of new materials and processes and introducing them to the industry. One of the materials that has caused a lot of attention in the past years was graphene, seen here in the background. Graphene is a 2-dimensional layer of carbon atoms arranged in a honeycomb-type lattice. Due to its structure and its low dimensionality, it is characterized by a set of unique properties, which make it very promising for certain applications in the electronic industry. Namely, we are talking mostly about high electron mobility, which translates into extremely high operating frequencies of graphene-based devices. However, despite years of development and a lot of hype that was going on in the media in the past decade, we haven't really witnessed any groundbreaking graphene technologies on the market. So what went wrong? Why aren't there any graphene technologies that could lead us to the 21st century? Well, the short answer is that commercial graphene that's available on the market in large quantities, so graphene that the companies will actually buy, it's not the same material as the material studied by the scientists in the labs. In general, it is characterized by low quality with many defects and discontinuities. Its parameters aren't really repeatable because every next batch of material will have slightly different parameters, which is a big problem for the industry. This is especially pressing in case of CVD graphene, which has to be transferred from a metal substrate to an insulator before the microfabrication process. Graphene produced on silicon carbide, which is the other main method of producing continuous graphene sheets, suffers from having anisotropic parameters as a result of presence of very high steps on the surface, which act as a barriers to the movement of electrons. To top it off, graphene is expensive and the lead times are very long. So here are a few examples of the benchmarking study that we did. Here's a microscopic image of the CVD graphene, which has a lot of discontinuities and defects, which make it almost useless for any applications. Here are the results of the commercially bought graphene on silicon carbide, which show a lot of defects, different pits, and many problems that it is facing, in addition to having very high steps on the surface, at least very high in the atomic scale. So for the past few years, I've been working on new improved methods that could finally bring graphene to the market. It is based on high temperature annealing of silicon carbide. In temperatures above 1400 degrees, its surface undergoes decomposition, and the silicon atoms, which are much more volatile, sublimate from the surface. This process is, however, very difficult to control. And the thing that helped me to let's say, harness it, to control it, was the discovery that it's actually reversible under excess flux from the external sublimation source. Using this newly achieved control of the process, I was able to produce near perfect graphene samples. You can see some examples here. Here's an AFM image showing that the steps on the surface are very low. You can compare it to the previous images that we've seen on the previous slide, and the STM image showing the true atomic structure of graphene and near perfect structure, basically. We are now co-developing this method with a spin-off company, BeeGraphene. The material that we are producing is characterized by very high quality with no defects and continuous coverage over macroscopic substrates. Its parameters are fully isotropic thanks to this limitation of step bunching that I've talked about before. What is really important is that the growth happens directly on an insulator, so there is no need to transfer graphene anywhere before the microfabrication. The process is very energy efficient and doesn't produce industrial waste, and the parameters are very repeatable. And finally, last but not least, the price is also quite affordable. So we are working on a few different applications that could demonstrate the feasibility of applying graphene to different sectors. Here you can see a video of a working OLED diode based on the graphene provided by us. Here are the microscopic images of the analog graphene transistors based on BeeGraphene. Here is an example of the first successful growth of two-dimensional molybdenum trioxide on graphene supplied by us to our partners. So we are working not only on improving our production processes, but also developing different applications. In this year, in 2021, we are focusing on moving the production from the lab scale, so from the scale of single centimeters, samples with the size of 1 by 1 centimeter, to the, let's say, semi-industrial scale of 2-inch wafers. In the next year, our main goal is to move towards the industrial standard of 4-inch wafers, which would basically enable standard industrial processing of graphene. So we hope that introduction of this process and its upscaling will help bring the renaissance of the Polish graphene, and which will then find applications in many areas surrounding microelectronic industry. What is important is that this time it's different than the last time that we were excited about Polish graphene, because this time graphene market is about to boom. Industrial analysts expect that 2021 will be the inflection point in the graphene market. So currently, most graphene is being supplied to the R&D centers worldwide, the basically scientists, both in public institutions and private companies. However, over the next few years, more and more industries will start adopting graphene processes. and it will find applications in sensors market, in analog electronics market, or for example, the rugged electronics market. So last thing to do is to thank my collaborators, Łukasz and Mikołaj, who are working with me in the process, and all the funding agencies which have funded this research from the very basic research of National Science Center to applied research, but by National Center of Research and Development. I want to thank you all for your attention. Feel free to drop me an email or to connect with me on LinkedIn, especially if you need graphene samples. We can find a solution to your problems. And I welcome any questions that you might have.
Thank you so much, Piotr. That's really interesting, and it's really cool to see the graphene development. And I'm actually wondering what changed actually in the previous time and this time that there is gonna be this graphene boom?
Well, to put it in simple terms, it was way too early in around the year 2010 to think about the actual commercialization, especially of, let's say, higher quality graphene. Because there are different types of graphene on the market, and while graphene inks or graphene nanopowders or solutions were quite successful and found several industrial applications, it was too early to introduce continuous graphene sheets that would eventually be used in microelectronics. So there are some companies who are doing that. They are mostly focusing on providing a material to researchers, but the actual industrial boom is about to start in the next few years.
So in the way the technology matured and now it's much easier to apply it?
Yes, that's true. So we have 10 or 15 years of R&D in how to apply graphene to different processes. It's a very challenging material to work with, and actually this adoption speed is not very slow. So silicon took a few dozen years to finally reach its way to real applications. But we are getting there. We are getting more experience with working with graphene. There are more and more graphene producers. And what's really important here, and what I try to stress during my talk, is that the graphene properties are starting to get repeatable. So if you get completely different material every time you order it, there's absolutely no way to introduce any industrial scale processes on it. Once you get repeatability and consistency, then you can start thinking about mass adoption.
Cool. We have one more question from Joanna Kwiatek. Hi, Piotr. What is the next application of graphene which you, BeeGraphene, want to investigate, apply? Thank you for your talk and good luck with your spin-off.
Thank you very much. So the question of graphene applications is always not that straightforward to answer. Because, as I mentioned before, we are working on continuous graphene sheets, which are a bit further away from the market. But one area that I find especially exciting and promising is rugged electronics. So the electronics that works in extreme environments, so in very high temperatures, in vacuum, under radiation, under extreme pressures. This is an area where graphene on silicon carbide could be used, because both these materials can basically work in 1,000 degrees in vacuum under radiation. So you can think about applications in space industry, in aerospace industry, drilling industry, or even sensors which are monitoring the industrial processes in situ, so inside the molten metal ponds, for example.